Oh, yes.
Hello, good morning. You have a homework due Tuesday. You'll still have a normal lecture on Tuesday. There will not be any what's that called practice session for the midterm or a help session for midterm, just because we've got only 2 classes in a week, we have to cover. So I'll keep moving ahead, but everything that is covered till today, which will be what will be used for the homework that is due on Tuesday, that's what will be covered in the exam. So midterm 1. And regarding lectures, lectures are getting recorded now. So this is what do you call lecture recording. So we have classes, these are the dates of the month and the day. We did not record on the first week. We have a recording here. This did not get recorded. So that's for your information if you're planning to use them, and hopefully everything works from this point on. That was just a error, so it didn't work out. I'll give links for the recordings on the web page itself, so that should be helpful. Currently, it appears as a YouTube playlist, which is probably convenient enough, but I'll give links to that on particular days if it is helpful at all. But currently, it exists in the sense that there is a link for the playlist in the web page. Okay. Any other comments or suggestions? Anything that you can think of regarding the midterm exam? Okay. We started on the idea of electric flux last time, and by the end of the lecture last time, we saw a pattern that always the electric flux across a closed surface, not across any surface. Electric flux is true or can be defined for any surface you can think of, but there are surfaces that are closed. Here is a classic example. It's a closed surface, and the electric flux coming out of a closed surface is always equal to the charge enclosed in it, in up to a certain unit that you decide to choose on. So this is converted into a law in the sense that every time we have measured this works out fine, and this is only another way of stating Coulomb's law. Coulomb's law is stated often as a vector equation. Force is equal to charge, multiply the charges and divide by r squared. It's the same content, but written geometrically. So a geometrical statement of Coulomb's law is Gauss's law. There's the same content in the of law. Let's write that geometric nature of Coulomb's. And by geometric, I mean it is the intuitive feature of that. Some often we have an intuition for a concept, which is often a more it's relatively vague word that you say is geometry. A quantitative version would be an algebra part that you really calculate things. So that's a very rough terminology there. And we introduced the idea of electric flux, and we said that a closed surface, this means that the integral is being done on a closed surface. So remember, area is a vector, it's not a scalar. So you integrate over the vector component of the area. So think of a sphere here. So that's your sphere, and think of a small element on the sphere, and this is curve, and you associate an element dA to that. The magnitude of this vector, infinitely tiny vector, is the area itself. That's the infinitely tiny area you can associate with that. and the direction is normal to the surface. Normal is if you make this small enough, even if it's a curved surface, once you go into an infinitely small area, that's relatively flat, that's perfectly flat in the perfect limit, in the sense of calculus, and in that limit, it is perpendicular to that rectangular area, which is flat in that case. A flat surface has two directions perpendicular to that. This is the one that is coming out of the, so once you think of a closed surface, it is the one that is pointing outward. That's the area A, and I use capital A and small a. Okay. So the same area I'm talking about, and then we have to integrate over all of that area. That's one way of proceeding, but we don't want to integrate over the area itself. Take the dot product of the area with the electric field at that particular point. At every tiny element on the surface, there is an electric field. Take the dot product of the electric field in the direction of the normal. Electric field could be anywhere. For example, it could be pointing outward somewhere here like this. Electric field that's pointing out here. It need not be directly coming out normally, but you're interested in the component of the electric field that is normal to the surface at that point. And you collect that. Remember, a dot product is always the component of the electric field in this direction, and you associate the area with it. And if you add up all this, remarkably, this is equal to the charge enclosed. Let me write that as Q1 plus Q2 over epsilon naught, and this is only the enclosed. Often this is stated as charge subscript enclosed, but I have written it explicitly as sum, so that you know that you are the sum of all the charges that is inside the closed surface. So this is a closed surface. So where are you integrating on? It's a closed surface, and these charges are all the charges that are inside the surface. If that could be many charges outside, it will be closer. The electric field does not care for or not the electric field, the total flux that is coming out does not care for the charges outside. So let's just demonstrate this, and this is a powerful law, and especially when there is a lot of symmetry in the problem, you can conclude about the nature of the electric field itself in a very simple manner. So let's the first time when I'm doing it, there will be a lot of assumptions involved. So I list them, so it will seem like it's a long logical train of thought, but once you take care of the assumptions in one place, it's only about 2 steps. So you have a symmetry, and immediately you can conclude about what will be the electric field for a certain configuration. So let's do the following example. So let's say uniformly charged a sphere, say off radius r. Remember that for a point charge, a single point charge, the electric field at an observation point r, let's say radius r, electric field at the observation point, so this is the observation point, is k times charge q over the distance from the center of the charge to the observation point, and the square of that and hat. I pointed out before that it does not seem like it depends on the radius of this chart. In fact, there is no reference to the radius of this particular chart. So it does not depend on that. So I can make this as big as I want, or I can make it as small as I want. In fact, I can make it infinitely small, and everything seems to be fine outside. Keep this in mind while we are doing whatever we are doing. Here we are saying uniformly charged sphere. This is also a sphere. Oh, that's here. A sphere, and let's say sphere is not precise enough, right? So let's say this is a spherical shell. So I think this is reasonably standard. Solid sphere is a material that is spherical in shape, like our Earth. It has content all the way to r equal to 0, and this would that's a solid sphere. And the spherical shell will be having mass only on a thin surface, infinitely thin surface at radius r. So that's the radius r, and it's hard to draw this if you want. Can you imagine this way? So a solid sphere is then you have the contact filled like solid earth, and color when it's an empty sphere. So that's as a spherical shell, unlike a solid sphere. I start with a shell because it's easier to deal with. It's uniformly charged, that means all the charges, there is not much space there, it is infinitely heavy, so all the charges are uniformly distributed on the surface. And just to emphasize that this is a shell, something like that. And it is infinitely thin, let's not have any thickness associated with that. And this is just an exaggerated version of the shell. So that's radius r. So that's the configuration we are talking about. And we are going to use the idea of Coulomb's law to talk about what is the electric field outside. What will be the electric field outside here? Any guesses? This is the point charge. For that, this is the expression, but it does not have any reference to the radius, right? By this, the point charge, what I mean is that it is spherically distributed, or we don't even say that it's a point charge. A point charge is by construction symmetric and from all directions. There is no an isotropy in there. So I could have extended this, since there is no radius r. I could have as well made it a spherical sphere of radius r, and this formula will change. So this outside turns out, we will prove this at this point very clearly. There is a chance that this point will exactly be the same as this expression. And so then the question becomes, what is the difference between a point charge and a spherical charge? But there is a difference. Any guesses on that? What will be the difference? If the expression for the electric field at this point, I'm emphasizing at this point, is exactly the same as this, what could be the difference? I'm saying that is it. Yeah. No, force is electric field times the charge, a second charge that you'll bring in, that will remain exactly the same. The question can be rephrased in the following way. Earth is very similar to this. It's just that we are talking about gravity there instead of electric field. Gravitational field somewhere at the position of the International Space Station. Will that matter whether Earth with the same mass is a spherical shell or a solid sphere? Do we know that Earth is a solid sphere or a shell? It might be empty inside. Is there an experiment you can do on the surface of Earth to check on the fact that, or to confirm on the fact that this is a shell or a sphere. Might have mentioned this before.
There's waves down,
Tell it again, yes.
like waves to see if it comes back or it like. You can tell it's like bouncing around again.
By waves.
I don't know, just like,
Sound waves? There are good points you have mentioned there, but let me state the following, since I want to emphasize a certain concept here. Use by measurement of gravitational field alone outside the Earth, there is no way you can make the difference between a solid Earth and an empty Earth with all the mass distributed around it. There is no way. You cannot design an experiment, and that's because there is no radius dependent. There is no geometrical parameter in there that tells us this. So the only way is to go in. If you go even a little bit inside, then you can tell it, and that's where the sound wave and the waves that I think you said that you got to go inside, so that is there, and that is how you do measure what's the content of Earth. You look for earthquake creates its own waves. It's not a it's a sound wave in a sense that goes through material, and on the other end you try to measure it and you look for that. But the point I was making is that you have to go in. Staying out, you cannot make out any difference. So I said staying here, the expression is the same. So apparently inside the expression will be different. Again, to give you the result already. So what will be the electric field inside? What is the gravitational field? If there was a spherically symmetric Earth, which is on a shell. If our Earth was empty inside, but perfectly spherically symmetric, and you jump inside that, will you get attracted towards the surface of Earth, or will you get attracted towards the center of the Earth? So center. Any other answer? Will it be towards the surface of Earth? So there is a spherical shell, and it bounces on. So if you jump into the Earth, what will happen? There is no force. The spherical symmetry for some reason balances out, and that's not convincing. I just stated that it's not convincing at all. So let's prove that. So the point is, if you were here, if you put in a positive charge or a negative charge here, the force it will experience will be zero. Right? Do you believe me? Right? So let's prove that. Right? So you shouldn't believe me. So it's not at all a trivial statement. So let's try to prove that using Gauss law. First, let's stay outside. So let's stay outside. Remember that Gauss law always assumes a Gaussian surface. Remember, Gaussian surface is not a real surface, it's an imaginary surface. We think it exists there, and so that we can do some calculations on that. Now, what about the electric field on that? So these are the assumptions that go in. So let's say assumptions. This is a spherically symmetric sphere, and if it is a spherically symmetric sphere, we are asked about what could be the electric field associated with it. Could there be a possibility that there could be an electric field? First of all, whatever is the electric field here, if we are not pretending that it is radially outward, if it is the electric field looks like this, it has to be the same everywhere. It should be like this, or it should be, and why is that? By spherical symmetry, what we mean is that you stand on Earth, whether you stand on the North Pole or on New York City or on Carbondale or somewhere else on the planet, everywhere, whatever you see should be the same. You should not be able to make out any difference. Usually we can, because there are stars that looks different from different places. So our universe is not spherically symmetric, but imagine a scenario where everything you look around, you cannot make out any difference. Think of a scenario where you come out of the house, whether you come from the front side of the house or back side of the house, that everything looks exactly the same. So that might be a weird feeling, I would think, that everything is the same. Probably snow day is probably an example where everything is covered. Imagine a situation where everything is covered with ice, it is white everywhere. And ocean might be a closest example, at least horizontally speaking, but always the sky gives it away in a sense where you can point out where you're exactly looking at the sky. But with that in mind, so if we stand here, that's the electric field, that it should be the same everywhere else. So electric field could be in this direction. But we know that based on other experiences, and especially there is another law which is saying that the curl of the electric field is zero, which we haven't studied. So the curl is how much the electric field rotates around this star. That's a separate law which we will see about 2 months down the line. Making that assumption in, remember that later on that will turn out to be when the magnetic field is on, that is not even true. So there is an assumption we are making which is coming from a future law, and it requires that the magnetic field is zero. It will turn out that electric and magnetic field are very closely related. If you change the magnetic field, you can disturb or create electric field, and one affects the other. So currently we are saying there is no magnetic field, which means that all these curves that you see, that circular piece that this component has, that is not allowed. So we are saying B is zero, and the assumptions involved, and which implies that no curve. This is not necessarily a familiar term. A curl means it should not rotate around the charge. Okay, so there is no curl of E. Which, if I remove that, if I require that condition now, what I'm saying is that that's radially outward. That's an assumption I'm making, that electric field is radially outward. Why should it be? Because I'm using something from a constraint that will come in, which will be more clear at a later stage. So in that sense, it's not a complete story, whatever I'm saying here. And you will see, and this is when you remove this constraint, that's what allows you to almost all our power generating mechanism. How do we get power from? Like a dynamo or a motor, all those things depend on this feature. Magnetic field is switched on. Always you will see that there is a magnet wherever a power is generated. Electric power is generated. Wherever there is a generation of electric power, most probably there is a magnet or a magnetic field. So that's that feature. Currently, I'm saying there is no source of electric power anywhere. And that requires that this is radially outward. This implies that E is radially outward. Okay. And the next thing is already we have said spherical symmetry, which means that E, the magnitude of E is only dependent on R, right? That is, it's not the direction that it depends on how far you're from the. That's the only quantity it depends on. Again, it's because of spherical symmetry. It depends on where you are, how far you're from the center, but it doesn't matter whether you're here, anywhere that's spherically symmetric. Those are the assumptions that go in. Together, these quantities mean that you have assumed the electric field to be, so it is radially outward, right? Radially outward. So that's a unit vector. And whatever is left out is the electric field E, the magnitude of E, And I'm saying it is only R dependent. It is not dependent on the angle, it doesn't depend on the latitude or longitude of where you are on Earth. It only depends on how far you're from the center. That for us, that's the radius of Earth. If you go farther for International Space Station, you're 300 or 400 kilometers farther. So that's your assumption. Let's see what we can conclude from this. So let's say R is greater than R. That's the radius of the sphere, and this means that you're outside the sphere. We'll come back and do inside. Remember, I claimed that inside it is 0. So while I'm doing this proof, if you get what I'm saying, if it is clear, then also imagine what will happen to that particular step if you're inside the sphere. We go with the Gauss's law. We are calculating the flux, electric flux on this Gaussian surface. Right, that is radius R. So this is radius R. Observation point is on the Gaussian sphere, and this is dotted with the electric field. E is equal to the total charge enclosed. How much charge is enclosed inside this Gaussian sphere? The total charge on this sphere. I have specified that. So let's say the total charge is Q. It is spread out on an area of 4 pi r squared. Everything, all the charge is on the surface of the sphere. So the charge density would be Q over 4 pi r squared. But let's stick to total charge. And that total charge is inside this closed surface. That's because in surface inside that, how much charge is there? That's the total charge on the sphere. I say that's Q. That's equal to Q. Right, that's your Q1 plus Q2 plus Q3. You have to add up all the charges. So that's your total charge in there. Use the geometry for us. I chose the Gaussian surface to be a sphere. That allows us to say that dA will be radially outward. Electric field, because of these assumptions, is radial. That's radial times E of R. It depends. This is a function of R. We are saying that this depends only on where you are. So it is an R dependent property, but R is fixed on the surface. So that will play an important role. This is 1 to begin with. The right side remains the same. There is only one step yet, right? So I started with Gauss's law, use my assumption that it is radial, the electric field is radial. This is equal to 1. Electric field is the same everywhere on this closed surface because it's the same distance everywhere and it's spherically symmetric. There is no angular dependence. So this immediately comes out with ER, electric field at the observation point, which could be anywhere on the Gaussian surface, times integral of the magnitude of the area elements is equal to Q over epsilon naught. This came out because it is spherically symmetric. Everywhere on that Gaussian surface, it's the same electric field I can bring out of the sum. It's like if you're adding a lot of quantities, you factor something out. Integration is nothing but a sum, so you can factor that out. So that came out. What is remaining is that a surface area of the sphere. Like this is the tiny element, that's the scalar value for that area. So that's the total area of the sphere. So that's 4 pi r squared. So electric field, E of R is times 4 pi r squared is equal to Q over epsilon naught. So you conclude that E of R, that is your derived expression. This was for a point chart, but you're not now saying for any shell, Q over 4 pi epsilon naught times 1 over R squared, which is nothing but K Q over R squared. Put it together with the R hat and you get this expression. Notice there is no reference to the radius of the sphere. I could be however far, however close, and I still will have exactly the same expression. I could be sitting on the surface and still I will not have the radius dependent on it. Any questions on those arguments that went through? With a logical argument, and often you will have to do this for a certain geometry that is provided to you. I will give you a surface or a solid sphere, and you will have to calculate what is the electric field associated with that. But that's good. This is nice. This is pretty much the same result we got. But I gave a very non-trivial result that inside the sphere, that's zero. The electric field is zero. How do we come to that? So now let's here, I said this is inside one. And it could be inside means it could be just infinitely tiny amount inside. It could be almost on the surface, but infinitely tiny close to that surface. So R is now less than R, capital R. What changes in the very first statement? First of all, I have to choose my Gaussian surface. I typically choose my Gaussian surface to be right where the observation point is. So let me choose my Gaussian surface. This is the new Gaussian surface. I choose it inside. That's a Gaussian surface. That's a new Gaussian surface for the new argument that I'm going to make of the surface. So that choice plays an important role. So you will have to get used to which surface should I begin with. If I choose that as my Gaussian surface, what's the right hand side? What is the charge enclosed inside that Gaussian surface? I heard zero, someone say zero, so there is no charge inside. All the charge is outside. So that's zero. And that's the important piece there. Just that observation that is zero will change everything now. This becomes zero. This is zero. Left hand side remains exactly the same. The same argument goes through. This remains 0, 4 pi r squared, except that now we are talking about a smaller sphere. Everything goes through. You reach here. When you divide out, you're dividing 0 over something, doesn't matter. So this immediately implies that electric field is 0 inside the sphere. Very strong logical argument that just by observing something on the right side, you immediately said that there are no calculation needed. That's the sort of intuitive power there. Okay. Any question for that? Anything that disturbs you? Okay, so if that is the case, we can now extend it, right? If the moment you get something non-trivial, you have to extend it, make it a non-trivial arrangement. Just not after you get used to this idea, okay, what's the big deal? It says spherical surface, inside it is 0, and you accept that fact after many years of if you do this again and again, you say, okay, so sphere, that's spectral geometry, so that's 0. But we can use this non-trivially now. Let's say, so this is a spherical shell, that's not even common. Earth is not at all. So what's the big deal? Or if it's a charged sphere in a lab, I'm never going to be able to make a shell out of it. It's too hard to construct. Most of the natural things are solid spheres. So can we have a solid sphere which has similar properties? Yes, there is. So let's think about that. So let's talk about a uniformly charged. Doesn't even have to be uniformly charged, I think. Yeah. It will turn out to be uniformly charged. Conducting, by conducting, I mean perfectly conducting a sphere. Uniformly is kind of not needed really, because if it's a conductor, charges are free to move around. If it's a sphere, if it's a perfect sphere, it will equally distribute it or redistribute the charge itself so that it's uniformly distributed. So now it's a solid sphere. This is a solid sphere. This is a perfect conductor. That's your radius r. This time I'm not making the restriction that this is a shell. This is a solid conductor. Say, think of a chunk of gold, and it is made out into a sphere. Gold is one of the very good conductors, so that's why I said gold. One of the, it approaches the perfect conductor limit. It's one of the highly conducting materials. Conductor, we remember from our perspective, even though you can give a more quantitative value to that, or quantitative meaning to the idea of conductors. So, but for us, it is the charges are free to move, and it's completely free to move. So, if you put a charge Q on this, the same amount of charge Q on it, since they are free to move, all the positive charges will try to stay as far as possible from them. They will invariably go to the surface. They have to, because they want to stay away from each other. So that's and then the question comes, how much to the surface are they? For example, you might have heard this before, that if you are inside a car and lightning strikes, is it good or bad? It's good, because it's a conductor, all the charges will stay outside. Okay, so it's okay if you're inside the car, that's the safest place for you to be if the lightning strikes. Totally better than outside, where there's a good chance that you will hit. And then you would say, then the question of what if you touch the surface of a metal? So the earth is a metallic surface. What if you touch it? Is there any chance that it might flow, it will penetrate? That means to say that these charges that I'm talking about, this is on the surface, how deep into the surface are they? Do they go 3 centimeters down? If they go 3 centimeters, car metallic piece is reasonably thick, and 3 centimeters might make it go through. But this is really tiny. For normal metals, this is in nanometers. Okay, it only goes nanometer deep. So that's something for you to realize. But still, I would say, don't touch anything. If you're really struck by lightning, don't take a chance. There is always, materials are not perfect, so the place where you touch by any chance, if it's not a good conductor, so don't do that. But you don't have much choice, right? If you're inside the car, at least your legs are touching it. So do whatever is more intuitive for that. But stay inside. That's not intuitive, but stay inside. Inside is more safer, apparently. According to theory, that's it's safer. Experimentally, there are many things that go wrong. So, but surely it is safer in that. Okay. So how is this now different? Notice I said it's a solid sphere. The big difference is that this is a solid sphere, and this was a shell. For a shell, it was understandable that all the charges are outside, and this was all outside, but now inside, because this is solid, what is the electric field inside? Zero again, because we can go through the same argument. So inside a conductor, electric field is zero. You will not feel any force at all if you were to put or if you stay inside. Electrically, it is completely inactive. you usually ask, how will you shield something? If you want to electrically protect yourself, you think that all the electric field out there, often you say electromagnetic wave, you don't like it, it is disturbing you, it is probably playing with your mind. How do you save yourself? The only way is to put yourself in a cage of conductor. That's called a Faraday cage. Right? Just basically a conductor. Take a can of what is it? Can, right? Food can, like that's metallic typically. It is small. Make a lot of take a big can and stay inside, and that's reasonably good protection for you from electric field. Only electric field and actually magnetic field also. For horticultural, it is perfectly safe. What happens is that even if there is a tiny hole, like often you have to say how good it is a Faraday cage. Let us say there is a 1 millimeter hole. That means that waves, usually electric and magnetic field, when they start interacting with each other, which we will come to later, that's what light is, or any radio wave is basically electric and magnetic field playing together. And their wavelength comes into picture. Wavelength is when you think of a water wave between two troughs or two valleys that are formed using a water wave. The distance between them is the wavelength. And for a light wave, it is really tiny. It is a nanometer. It is actually about 500 nanometers. It could be anywhere between 400 nanometer to 700 nanometers. That's what decides the color of light. And that distance matters. So if you're making a cage and you want to protect yourself from light, then you want to have that cage have holes that is smaller than the wavelength. If you want to talk about radio waves, it's very easy because radio waves have wavelengths in centimeters, often kilometers, right? If it is an amplitude, a modulated wave, then it is in kilometers. FM is in centimeters. So if you have a cage that is smaller than centimeters, then you're proof with radio waves. That's why your cell phone doesn't work inside an elevator. Often concrete buildings have metallic rods inside their structure, and that's why you don't get cell phone signals inside those buildings. Usually government buildings are concrete, and inside concrete there are metallic rods, and that's why you don't get signals inside. Elevator is a good example. That's metallic typically. It has a lot of metal abuse, and your cell phone do not work very well. More modern cell phones use wavelengths smaller also. That way they can get away with it. Inside a car, how do you get cell phone signals? That's pretty much metallic, but there are these windows in there that's helpful. Earlier you used to have antennas on top of this, on top of cars, but more modern cars, I think, have smaller antennas. It's not no antennas at all. No, still, at least my car has an antenna. Not I know you want to. Okay, so anyway, so again for a conductor, electric field outside, if it's a straight or distribution, it is the same thing again. It's exactly the same thing. A times Q over R squared and R X outside, and 0 inside. So notice how I went from one geometry to the other. This I took some time to understand, but once I understood this, I made a jump over to a solid sphere, and the same argument goes. But now I'm going to make a jump to a non-trivial geometry. Let's say any conductor, any arbitrarily shaped conductor. Shapes connectors. So let's think of a very weird shape. So it's having no clear, simple geometry. And again, let's put a charge Q on it. And again, we would like to know what is the electric field outside and what is the electric field inside. Outside turns out to be hard. The shape is not easy, so you have to do integrations. It's not zero, so it is outside. So this is hard. It depends on the geometry. So if the geometry is not a convenient geometry, it is hard to evaluate. So probably it won't be asked in your exams because hard problems are not given in exam. Solvable problems are given, right? But what about inside? Inside is easy. Why is it easy? Again, I need a Gaussian surface. This is true for any surface, any closed surface. Any closed surface, this is true. I just have to think of a surface which is convenient. So I take a surface, I said charges are placed 1 nanometer inside connector. So I go that close. So that's my Gaussian surface. I go all around on that surface. That's a closed surface, and of course, this comes out of the board, and that's a closed surface. Right side, is there a charge enclosed? No. So that's zero. Same argument goes for except that this is not a spherical surface now. Right side is zero. So electric field times radius, whatever is zero, but the area itself is not zero. So the electric field has to be zero. So inside a conductor, always it is zero. It doesn't have to be spherical. That's like thought. You might have thought that, oh, you did this for a sphere and you're asking me to sit inside a car and not worry. That's not the same mathematics, but it goes through because of this reason. Gaussian surface does not use that spherical geometry at all. So everywhere inside a connector, electric field is zero. A very strong statement which will be used all through in the course whenever connector. I won't bother to write perfectly connecting. We will always, whenever there is a connector, unless it is specifically mentioned, we will presume that it is a perfectly connector. Similarly, whenever it's an insulator, we will assume that it's a perfectly insulated. That means they really cannot move around. Usually, in real life, things in between, things can move a little bit. You can polarize things inside material. Having done this, now let's do an exercise where this is actually a solid sphere, and the charge is now everywhere around inside the solid sphere. So it is like the solid earth that we have in real life if you are thinking of gravity. And in this case, we are talking about a proton. And now this is a solid sphere. And let's think of an atom. What is an atom made of? These days, we take it for granted. Right? We all know what an atom is. We study it very early in some grade. What is the atom made up of? Charges, protons and electrons. Correct? How big is the proton? Very tiny, right? So usually this is a proton and an electron is really far away. Right? This is like pretty much like a Jupiter, or probably even farther than Jupiter. So this is about, this radius is 10 raised to minus 15 meters. And this is the radius of an atom. That's 10 raised to minus 10. Notice the scale. That's about less than a nanometer. You have to go a million times smaller to reach the proton surface. How do we even know that that's true? Right? The textbooks, right? Surely. But we take it for granted that that was the model all the way, but it was not. Until 100 years back, we didn't know that. just 100 years back, 100 years is not very far away, until 1910, it was not known that proton is this tiny. Until 1910, that's not very far away. Right, appreciate that. We had a lot of physics going on at that time. Already Newton has been there for a significant amount of time. Already electricity was going on. Faraday was there in 1810 and so on. So already a lot of electrical devices that were being used around. There was a lot of technology already existing, but we did not know that proton was this size. In 1910, the model of an atom was, this was the model of atom. The negative, 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 that's how equal amount, right? 4, right? No, 5, right? 5, equal amount of charges, and you just had a lot of positive charges and a lot of negative charges, and they called it a plum pudding model. Like probably read this before. It was called plum pudding model, probably something related to the food and some cultures. Okay, but how do we know? Go from here to there, and let's again use Gauss's law and how conclusive it is. And I will make a hint on this. We have a very similar problem existing today. Existing today, there is an unsolved problem. Remember, in 1910, this was the model of an atom, and there was an experiment done, and it was realized that this couldn't be true, which is what I'll illustrate now. In detail, I will illustrate how this cannot be true. But in gravity, there is a very similar problem that we believe, based on a lot of experiments, that our universe is expanding. Everything we see around seems to be going away from us. Right? That's okay. We have got to accept that. Experimentally, that has been going on for 100 years. We see that, oh, that's perfectly correct, and we have a good explanation for that. We seem to understand that. But more recently, in the last 20 years, it has been realized, or it has been observed, that it is not just expanding. Expanding was okay, but it is accelerating while expanding. It is not slowing down. Expansion can happen in 2 ways. You're going away from the home, from your home. One way is that you're speeding up while you're going away. And the other is that you're slowing down while you're going away. It was expected that you will be slowing down. It was expected that the universe is expanding, but it is slowing down while it is expanding. Why? Because everything is being pulled by gravity. There is nothing as powerful as gravity at that scale. All electricity, everything goes out of window, nothing, it's all negligible. Gravity is the only strong force we can think of at that scale. And the expectation was gravity is always attractive. So when something is going away, it should slow down. Right? It should slow, but it turns out experimentally that it's accelerating, which means that we are missing. There must be something else around here which is actually repelling, and we have no idea of what's going on. Like it's absolutely no hints at all. And you should compare that with this, and I'll give a small hint on how the problem is very similar, but exactly in the opposite sense. That was repulsion. Here it is repulsion we're talking about, and gravity here. Now we want to talk about attraction. Okay, so we are talking about an atom. So take that particular atom. Let's say this is our 1910 model, and it's very easy to remove these electrons. You can ionize atoms very easily. You just put them in a box, heat them up. They start coming and colliding with each other. Remember that you cannot play around with one single atom. You have to work with 10⁻23 of them. You take a box of atoms, basically a gas, and you heat them up. Right? When you heat them up, they start moving around and bouncing off each other. Every time they bounce off, they lose some electron. And if you sufficiently bounce off electron, then if there is a mechanism where you can pick the electrons, you can actually put some positive charge, come up with a mechanism where all the negative charges are moved around, or there is a filter associated with that. If you can be clever there, then it is easy to, or it was already realized how you can go from atom to an ionized atom. So you have only positive charges. That was easy to perform. By 1910, they were very good at these things. So we have a positively charged sphere of radius r. That's what we want to work with. And it is uniformly distributed. That's an assumption we make here because we don't know anything about the proton. But let's say there is a uniformly charged sphere of radius r. That's radius r. And there is Q charge in there. And again, we want to find out what is the electric field outside. If let's say the electric field is assumed to be going out like this. That's an assumption that it is radially outward. And make a Gaussian surface, let's say outside is. First, let's talk about outside. And that's that. And now we are outside. And R is less than outside is greater. R is greater than R. And that's your R. Outer observation point is outside the sphere. Same argument. Gauss's law. EA started with E is equal. How much charge is stored inside the sphere? Same argument. Q over epsilon naught. Again, break spherical symmetric. Same argument goes through this console, radically. R cancels with this. Immediately you conclude that E is equal to 4 pi r square coming from the area. That's Q over 4 pi epsilon naught over 1 over R square. And this only gives me E. And the electric field is R hat. And when I don't write the vector sign, I mean the magnitude of that vector. Outside is simple. Again, it is the same. I made a statement earlier that sitting outside, we can never find out what's the structure of that of our Earth, or in this case, the atom. And that's why you have to construct this very expensive accelerators so that you can bombard your proton so that you can see inside it. You have to go inside. So now let's go inside the sphere. And the only argument that changes is Q, right? Well, how much charge is enclosed? Now we are talking about inside. So my Gaussian surface is somewhere here. That's my radius mu configuration, that's my radius R. Observation point is now here. Is that charge inside this? That's not. No, there is charge, right? I said it's a solid sphere. And charge is inside the sphere. Right? So you have any confusions there? So now this time there is a charge there, and then we are asked how much charge is it? Right? But that's a ratio problem. If you have a sphere of radius r, you have a sphere of another radius r, if they are uniformly charged, then the bigger radius will have not just the double. If you double the radius, it's not the doubling that happens, it is Q. Right? So it's a ratio problem. So charge enclosed, let me do that here. So charge enclosed over the total charge. So that's Q, total charge on the sphere. That's the same as the volume, right? It's a density that's the same. So charge per unit volume, or maybe I could write it in this form. The density is the same, it is uniformly charged enclosed by the volume, which is 4 pi by 3. It is the observation for R2. Right? That's the volume of the sphere that we are talking about, enclosed sphere, and that is the total charge on the sphere whose volume is 4 pi by 3. capital R cube. Since the density is the same, when we say it is uniformly charged, I can pick any two volumes and do that ratio. And this means that these two are the same, and immediately say this cancels out. So Q enclosed, which is what appears here, is equal to the charge itself, original charge, but that's not equal to, that is a ratio, which is Q. For example, if this was half the radius, then it is charge is not half, it is 2 raised to Q. So it is only 1/8 of the charge that is there in half of the radius, which we learned very early how the power dependence works. So here on this side, this is charge Q, and this is R Q over capital R Q. Notice now the capital R has come into picture. Right? Until now, the radius of the sphere was not coming into the picture. And now we have the radius of R. That means that we can tell something about the proton radius. Right? This R is the quantity we are talking about. That's the radius of the proton if this was the proton. The left side argument remains the same. So it is E times 4 pi R squared, which is Q over epsilon naught times R cubed over capital R cubed. Observation point inside the sphere, radius of the sphere, both are coming into picture. Left hand side has the R square coming from the surface area. Right side has the R cubed coming in from the fact that the total charge is scales as the volume. So that volume goes down. It doesn't linearly go down. It goes as a cube of the radius. Put this all together and we immediately say that the electric field, which has this R hat in it, 4 pi epsilon naught still is there, Q over 4 pi epsilon naught. And this R square cancels one of the R's, and the observation point now is in the numerator over R cubed. And that's the electric field. Remember, electric field was 1 over R square when you're outside. But when you're inside the sphere, it is linear. It is in the numerator. Which is good because as we go to 0, if you had used this formula, you should have bothered about it before, that what happens to the electric field right when R is equal to 0. Using this, it's, for example, for a point charge, it really goes very, very high. And it goes to infinity in the true sense, if you can really go to 0. But now it is better, as R goes to 0, electric field is 0, so you don't have to at least deal with infinity. It's harder to deal with a very large number. That's a good feature. So electric field slowly increases until it reaches an R value, and then it starts decreasing like 1 over R squared. So let's put this all together. How does this look like? So if I were to plot the electric field as a function of the radius R, right? Somewhere here is the radius of the sphere itself. Think of it as the radius of the proton. And how does it go? So that's the reference point here. Let's say it for R equal to 0, you're inside. It is 0, it increases to a certain value. That's linearly increasing. So it is 0, electric field is 0, grows linearly, straight line. And then after it reaches the surface of the sphere, it starts dropping, but not linearly, it is quadratically in the denominator. So that looks like this. And it keeps going forever till there. So this is 1/r², and that's r. And at this point here is k³ over r². The radius shows up. So the surface, how much electric field is there on the surface, gives you an idea of how much is the maximum force something else will experience. This is the maximum. It's like saying Earth, if you come very close, the force of Earth is very large, but then you would think that as you keep going inside the Earth, the force should increase. No, because after that, the outer shells stop contributing. So your mass is also decreasing. So right at the center of Earth, what is the force you would experience? Right at the center of the Earth, what is the force you would experience? Zero electric field or gravitational field is zero. Right at the center of the sphere, electric field is still zero. The force experience will be zero. Again, by symmetry, you can see that everything else is going in the same direction. So that's an easier understanding to have. But it is not very clear whether it's stable there or not. Is it disturbing the level? Is it going to fly away or not? But in this case, it turns out that it is stable, and this is electric field is zero. You know how much force it will exert on, and so that experiment design was that you make a small beam of a positive charge, so beam of positive charge, and you kept a gold foil there. By gold foil, what it means is that you put a lot of protons. And there is a lot of these charged spheres are there. This is the gold nucleus, if you want, and you take another positive charge. You use helium atoms, positively charged, and you come and bombard. Question? Comment? No? Okay, that helps. Okay, so again, there is a positively charged big sphere, gold nucleus, and you bombard it with another small, tiny nucleus, again positively charged. Two positively charged, they don't like each other. So you really need to shoot it. It's like almost shooting a bullet at someone. If you are repelling, so you really need to force something into that. So a positively charged particle is forced into that. And you have to estimate, you have to make an estimate as to how much should be the velocity of this, so that you can cross that field. So that is a shield here, because in the sense positive charges, you don't want to be close to me, but that's your maximum value. So Rutherford calculated that and said that, oh, that's what I expected. That's the maximum force I'm going to expect. But he had a velocity much larger than it. So he thought he's going to really bombard this, and the positively charged particle is going to go through that, and all these atoms should be broken in a sense, or they should break apart. But what happened is, so it's like saying this is a value if you have a positively charged particle, if you have a lot of energy, it will be here. I think of that it has velocity can be converted to energy. So there is a lot of energy in here. So you already can cross this significantly. So they're expected to go into the atom. But it turned out that in experiments, it did not go through. Instead, it reflected back, which means to say that the only way you could have explained, or one of the ways you could have explained, is that this is not here, this was here. That's our point after 1910. That means that you go linearly up. So you go up here, and then you come down. So that's electric field very large. Just by making the radius small, you have changed your electric field. If you make it smaller, your R square has gone significantly larger, and the electric field is significantly, it's not linearly increasing, it has gone up. And if you go billion times smaller, that's square that makes it 12 times larger. You were nowhere close to that, so all the beams that would be shot on the gold nucleus, they all came back, and its interpretation was that we expected it to be like a bullet crossing a sheet of paper. Instead, all the bullets came back and hidden back. So that's the way you explain why your proton nucleus is so large. And this is our prime now. This is the current status. It's 10 raised to minus 15 meters. Electron radius is significantly smaller. It's about 10 raised to minus 18 meters. But that is only a projection. We really cannot reach that radius. We only know that it is smaller than 10 raised to minus 18 because we cannot reach 10 raised to minus. That's the maximum we can reach. With our technology, we can only reach distances about 10 raised to minus 17 meters or so. So that's atom, but I suggested that there is a similar thing going on in our universe where everything is getting repelled. In 2 minutes, let me summarize that. So in our universe, think of it as a simple way of looking at it is if you have two masses M and you put a spring in between, the spring is not important, they are connected. If you push them and release them, they will go away from each other, but there is a gravitational force between these two masses. So there is a velocity v, but there is a gravitational force v that is acting to the left, so they should slow down. So that it is moving away, but it should slow down. But it turns out that it is increasing. So that's our universe going down. But now let's measure velocities in galaxies. So let's say there is a galaxy here. A galaxy now, very simple approximation. Galaxy is not always perfectly spherical. There are stars moving around. You can measure the star velocity. You can do precise measurements these days and measure the velocity of stars, and you can plot them. So this is radius and this is velocity. Velocity is very related to electric field, how fast the star is going around, how fast the planet is going around the sun pretty much decides how much is the gravitational field. That's completely decided by the gravitational field of the sun. It turns out it is very similar. It's expected that as you go away, its mass is decreasing and the velocity is expected to do this. Very similar to that. So this is the theoretical curve. So this is theory. And galaxies, you can do diagrams very easily, these days very precisely for almost all galaxies. It turns out that the velocity of the stars do very well here. Notice here the data was off for small radius. Here it goes very well here, but as you go farther, it doesn't match. The data is here. Right, so for larger radius, it doesn't seem to be matching. And the point is, how can you explain that? What can you do? Here the answer was very straightforward, and at least immediately someone came up with a suggestion that, oh, it must be small radius. But is there a way of explaining this data just by saying, oh, our galaxy must be having something? The idea suggested is that there is matter here which we don't see. And that's what is called dark matter. But that's very speculative. With that, I'll stop. And thank you.